Hello everyone, I'm Christina and welcome to this video for A-Level Mathematics Calculus series. This is video 23 and we're differentiating our exponential functions e to the x and a to the x, and this is part 2. So the objectives for this video are to differentiate y equals a to the kx. In the last video we differentiated y equals a to the x, so now we have this added k constant. And then we're going to use that to work through another example. So to differentiate y equals a to the kx for this function, it's very similar to what we had before. So we have our factor of ln a, and then we have our original function back. But we have to bring out our constant k in front. So for y equals a to the kx, our first derivative dy over dx is equal to k times ln of a times a to the kx. So now let's use that to work through our second example here. We want to find an equation for the tangent to the curve y equals 3 to the power of 2x at the point 1, 9. So we have our y here. What we'll want to do first is find dy over dx, as this is our first derivative and our gradient function. So how will we differentiate this? This is equivalent to our a being 3 and our k as 2. So if we compare it directly, I can write it here. A is a kx, where a equals 3 and k equals 2. And so when we compute dy over dx, let's just refer back to this. That's going to be k ln of a times a to the kx. So that's k2 times ln of a is 3, times a, that's 3 to the power of kx, that's 2x. And so we can write that there. Now, what we want to do is find the equation for the tangent to the curve at y equals 3 to the 2x. So we want our gradient here at this point 1, 9. So what we're going to do is substitute our x coordinate into our differential function to get the gradient at that point. So dy, let's put at 0.19, dy over dx is equal to 2 ln 3 times 3 lots of 2, 3 lots to the power of 2 times 1. That's our x coordinate there. And so we get 2 ln of 3 times 3 squared. So that's 2 times 1, that's 2. So 3 squared, that's 3 times 3. So that's just going to be 9. So that's 18 ln 3. So that's our gradient now. And we want the tangent. So the tangent is a straight line. So our general equation for a straight line, so I'm going to put tangent in brackets because that's the straight line we're looking for, is going to be y minus y1 equals m x minus x1, where m is the gradient, which we've just calculated. That's 18 ln 3. And we can substitute in our coordinate 1, 9 for the y1 and x1 values. So y minus 9, that's our y coordinate for our point given in the example, equals 18 ln 3. That's our gradient that we just worked out from our first derivative function. And then we have x minus x1, or x1 for our coordinate is just 1. So that's 1 there. And if we multiply this out, we can get our equation of a straight line in the form y equals mx plus c. So let's do that. So we have y minus 9 equals 18 ln 3x minus 18 ln 3. let's move the -9 here onto the right-hand side. So that's equals 18 ln of 3x. So let's put the x at the front. Typically, that's how we write it. So we can write it as 18x ln 3. So that's not ln of 3x, that's ln 3 times x. So I'll just put those in brackets there. Minus 18 ln 3 plus 9. So then y equals 18x ln 3. We can write it as plus 9 minus 18 ln 3, like that. But here we can see that this is going to be our plus c. We had our m here. That's our mx. So then this whole thing is our mx. And so now we have the equation of the tangent in the form of y equals mx plus c. And we've completed example 2.